On June 21, 1943, the flight deck of the United States Navy training carrier USS Wolverine was a platform of unforgiving geometry. It operated on Lake Michigan, not the Pacific Ocean, and it served a single industrial function, which was the conversion of novice aviators into carrier-qualified pilots. The aircraft approaching the deck was a Vought SB2U Vindicator Bureau number 1383. It was a machine caught in the transition between eras. It possessed the monoplane wing of the modern age, but retained the fabric-covered rear fuselage of the biplane era. This specific airframe was not destined for combat. Instead, it was destined to become the subject of a forensic recovery operation nearly half a century later. The pilot at the controls was Second Lieutenant A.W. Lemons. His objective was a standard carrier qualification trap. In 1943, the process of landing a carrier aircraft weighing well over 6,000 pounds on a moving deck was not automated. It was a manual coordination of energy management and visual signaling. The carrier qualification procedure required the pilot to fly a precise glide slope governed by the landing signal officer stationed on the aft port corner of the flight deck. The signal officer communicated strictly through paddle positions indicating altitude and speed corrections. The pilot had to balance the aircraft on the edge of a stall, maintaining enough lift to control the descent, but little enough energy to stop within the arresting gear wires. The Vindicator was powered by a Pratt & Whitney R1535-96 twin Wasp Junior engine. This 14-cylinder radial engine generated 825 horsepower. On this specific approach, the energy equation failed. The aircraft settled too low or drifted off the center line. The evidence suggests the aircraft stalled or was waved off too late to recover flying speed. It did not strike the deck with catastrophic force. Instead, it departed the flight deck envelope and settled into the water immediately alongside the hull of the carrier. The impact was an energy exchange between a slow-moving airframe and the surface of Lake Michigan. The structure did not disintegrate. The pilot survived the water entry and was rescued by the plane guard vessel. The aircraft, however, lost its buoyancy battle rapidly. The Vindicator sank through the water column. It came to rest on the lake bed in a depth of 130 feet. The loss was recorded in the daily log of the Wolverine, and the training squadron simply wrote off the asset. In the context of 1943, losing a training airframe was a statistical cost of doing business. The Navy had thousands of aircraft, and the war effort required pilots more than it required the recovery of a single obsolete scout bomber. Bureau number 1383 was struck from the inventory. The significance of this specific loss was not apparent in 1943. The Vought Vindicator was already being phased out of frontline service, replaced by the Douglas Dauntless. Most Vindicators were scrapped or destroyed in combat during the early battles of the Pacific. By the end of the war, the type had effectively vanished from the inventory. As decades passed, every other example of the SB2U series was destroyed or recycled for aluminum. By 1990, the aircraft sitting in the silt off the coast of Chicago was no longer just a lost training asset. It was the sole survivor. It was the only complete Vought Vindicator in the world. The technical identity of this aircraft defines the engineering challenge of its recovery. The Vindicator was designed in the 1930s when aviation technology was shifting from wood and fabric to all-metal stress skin construction. The forward fuselage and the wing center section were metal. The fuselage aft of the cockpit relied on a steel tube framework with fabric covering, while the wings were primarily metal structure with fabric-covered sections and control surfaces depending on station and variant. This mixed construction created a structural discontinuity that would dictate every decision made during the recovery. Metal corrodes but maintains rigidity. Fabric rots and loses all tensile strength. In a typical saltwater environment, the fabric sections would have been consumed by biological organisms within a few years, leaving only the steel skeleton. Lake Michigan imposed a different preservation regime. Cold, fresh water at depth slowed the destructive clock just enough to keep the structure recoverable, while leaving the team with a more difficult problem, lifting an artifact whose most fragile surfaces had survived. In recovery terms, the cause is secondary. The governing variable is condition. The aircraft went over the side largely intact, and decades of immersion turned material fragility, not pilot technique, into the real engineering problem. In 1990, the objective was absolute: retrieve the airframe for preservation. But the materials turned retrieval into a rigging problem, not a lifting problem, and the team could not afford a single contact error on the fabric-covered structure. The recovery of Bureau No. 1383 was not a salvage job for scrap metal. It was a retrieval of the last verification of a specific design era. The Vindicator represented the moment the Navy decided to move to monoplanes. Its structure held the answers to how that transition was engineered. The survival of the fabric was a hypothesis that could only be proven by bringing the machine to the surface. But to do that, the team first had to understand exactly what the lake had done to the airframe over 47 years of immersion. While the loss was a standard training accident, the environment it fell into would create an unprecedented engineering opportunity 47 years later. From June 1943 to June 1990, depth and temperature did what war could not. They slowed change. At roughly 130 feet and 39 degrees Fahrenheit, the lake held the airframe in a stable, low-energy environment, favorable by underwater standards but still material-dependent. To understand why the Vindicator survived when thousands of other combat aircraft dissolved into iron oxide, one must understand the physics of the water itself. The primary enemy of submerged metal is chloride. In the oceans, the water acts as a highly efficient electrolyte. It facilitates the flow of electrons between dissimilar metals connected by a conductive path. An aircraft is a battery of dissimilar metals. Aluminum skin, steel spars, magnesium fittings, and brass bushings react aggressively in salt water. This process, known as galvanic corrosion, eats the structure from the molecular level up. The aluminum turns to white powder and the magnesium components simply vanish, often leaving gaps where controls used to be. The ocean does not negotiate with aluminum alloys, it consumes them. Lake Michigan operates under a different set of chemical rules. The water is fresh, it lacks the dissolved salts that drive rapid electrolytic reactions. While corrosion in freshwater is generally slower than in seawater, decades of immersion still impose severe cumulative damage, especially to steel components and any organic coverings. The water at 130 feet sits below the thermocline, the boundary layer that separates the warmer surface water from the cold deep water. In this deep zone, the temperature is locked at roughly 39 degrees Fahrenheit, which is the point where water is most dense. This low temperature acts as a refrigerator, slowing down every chemical and biological reaction on the site. The mechanism of freshwater preservation extends beyond metal. The most vulnerable component of the Vought Vindicator was the doped linen fabric covering its aft fuselage and wings. In a warm, oxygen-rich environment, bacteria and fungi consume the organic fibers of the linen. In a high-energy environment, currents shred the fabric. But in the deep, silent cold of the lake, the biological consumption rate drops to near zero. The silt at the bottom creates a secondary seal. As the aircraft settled into the lake bed, a fine layer of sediment drifted over the wings and fuselage. This silt is anaerobic, meaning it contains almost no oxygen. It buried the lower sections of the airframe, effectively vacuum sealing them against decay. This environmental seal created a time capsule effect that defied standard marine salvage logic. When the recovery team eventually reached the aircraft, they found the fabric skin was not just present, it was chemically active. The distinct smell of the nitrate dope used to tighten and waterproof the fabric in the 1930s was still trapped inside the structure. The cold water had arrested the off-gassing of the volatile chemicals. The aircraft did not smell like pond water or rot. It smelled of an active airfield in 1943. This sensory detail was a fringe indicator of the total arrest of decay. The preservation of the paint and markings provided a level of forensic clarity that is usually lost. On the side of the fuselage, the code 9B12 was clearly legible. This marking identified the aircraft as belonging to Bombing Squadron 9 before it was transferred to the Carrier Qualification Training Unit. In a saltwater environment, marine growth like barnacles and coral concretions would have obliterated these surface details within a decade. Here, the paint was merely covered by a thin film of dust. The preservation was so complete that it created a structural paradox for the engineers. If the fabric had rotted away, the recovery would have been a simple matter of lifting a steel skeleton. Chains could be wrapped around the tubular frame without consequence. But because the environment had preserved the linen, the aircraft remained a complete aerodynamic volume. This meant the fabric was now the critical constraint. It was 47 years old. While it looked intact, it had lost much of its elasticity. It could not support the weight of the water inside the fuselage if the plane was lifted incorrectly. The preservation had saved the history, but it had complicated the physics of the removal. The wreck sat upright on its landing gear, settled into silt rather than hard bottom. The airframe behaved less like dead scrap and more like a balance system embedded in a semi-solid medium, an important detail for breakout and stability. At this depth, light and visibility can be extremely limited, often functionally dark, especially when silt is disturbed or conditions are turbid. For nearly half a century, the Vindicator sat in total blackness, invisible to the surface world. It was not lost in the sense of being destroyed, it was misplaced. The lake had frozen the aircraft in time, protecting it from the atmosphere and the sun and the biological scavengers. But this protection came at the cost of accessibility. Locating a 42-foot wide object in millions of acres of dark water required a different set of tools than visual spotting. The lake had done its part to save the machine. Now the engineers had to find a way to see through the dark water to locate it. In 1990, the National Museum of Naval Aviation contracted A&T Recovery to locate and retrieve the lost Vindicator. The operation began with a fundamental constraint. The search area was measured in square miles of featureless lakebed, while the target was a collection of aluminum and fabric measuring 42 feet across. In the zero visibility conditions of the deep lake, visual search was impossible. A diver or a camera could pass within 10 feet of the wreckage and never see it. To find the aircraft, the team had to rely on sound. The primary tool for this phase of the operation was side-scan sonar. This technology solves the problem of opaque water by replacing light with acoustic energy. The system consists of a tow fish, a sensor pod dragged behind the survey vessel on a long cable. As the vessel moves along a pre-planned grid, the tow fish emits pulses of high-frequency sound in fan-shaped beams to the left and right. These sound waves travel through the water and strike the bottom. When they hit the mud, they are largely absorbed or scattered. When they hit hard man-made structure like an aluminum wing or a steel engine block, they bounce back to the sensor. The resulting data is not a photograph, it is a map of acoustic reflectivity. The operator on the surface sees a scrolling waterfall display where the lakebed appears as a textured gray plane. A wreckage field appears as a hard, bright return followed by a distinct acoustic shadow. The shadow is crucial. Just as a building casts a long shadow in late afternoon sunlight, a shipwreck casts a sonic shadow where the sound waves are blocked. By measuring the length of this shadow, the team can calculate the height of the object protruding from the silt. The geometry of the return separates geology from machinery. Nature rarely creates perfect straight lines or right angles. The survey required a methodical mowing of the lawn. The boat drove parallel tracks overlapping the sonar coverage to ensure no gap existed in the data. This process is tedious and binary. For hours, the screen shows nothing but the monotony of the lake floor. Then a specific anomaly appeared. It was a coherent shape with the hard return of metal and the dimensions of a tactical aircraft. It was not a scattered debris field. The target was intact. Verification followed the acoustic detection. The sonar contact provided a location but not an identity. To confirm the target was BuNo 1383, the team moved from sonar contact to on-site inspection and cross-referenced the wreck with recorded loss data. Positive identification relied on recoverable identifiers matched to the historical record. Not a single dramatic reveal in the dark. As the vehicle descended, ambient light collapsed to zero. Identification would come only from what the lamps could carve out of the silt dark water at close range. The first visual contact confirmed the sonar data. The aircraft was sitting upright. The wings were level. The freshwater preservation described earlier had held the structure together. But positive identification required more than just recognizing the shape of a Vindicator. The team needed a serial number or a unique marking to prove this was the specific airframe lost by Lieutenant Lemons in 1943. The camera manipulated by the operator on the surface moved along the fuselage. The fabric skin, which should have been shredded or rotted, appeared smooth. Then the lights caught a sequence of characters painted on the side of the fuselage, 9-B-12. This code was the squadron designator for Bombing Squadron 9. Records confirm that Bureau number 1383 had served with VB9 before being transferred to the Carrier Qualification Unit. The presence of this specific marking was a definitive forensic link. It connected the object in the mud directly to the historical record of the aircraft transferred to the training command. The survey also revealed the condition of the airframe in relation to the sediment. The aircraft was not just resting on the bottom, it was partially integrated into it. The landing gear struts were buried up to the axles. The bottom of the fuselage was settled into the silt. This meant the aircraft was subject to suction forces. The mud had created a seal around the contact points. If the team attempted to pull the aircraft straight up, the suction would add thousands of pounds of resistance to the lift load. This resistance could exceed the structural limits of the airframe components. The inspection confirmed the integrity of the aircraft, but it also highlighted the fragility of the prize. The doped fabric, while visually intact, was not structurally sound in the same way it had been in 1943. It was brittle. It could verify the identity of the plane, but it could not bear the load of recovery. The team could not simply hook a cable to the tail wheel and pull. Such an action would rip the tail off or strip the fabric skin entirely. The identification phase concluded with a verified target and a verified set of constraints. They had the right plane. It was in the best possible condition for a 50-year-old wreck, but it was trapped in the mud and built of materials that required a touch gentler than any standard salvage crane could provide. With the target identified, the engineering challenge shifted from finding the machine to moving it without destroying its most fragile component. The engineering challenge of retrieving Bureau number 1383 was defined by a single negative constraint. The recovery team could not touch the aft 40% of the aircraft. In a standard salvage operation, the method of lifting a submerged object is brute force. Steel cables are wrapped around the fuselage and the wings, creating a sling that tightens as the crane pulls upward. This technique relies on the structural integrity of the target to withstand the crushing force of the cables. For the Vindicator, this method was a guarantee of destruction. The doped fabric covering the rear, fuselage, and outer wings had survived the chemistry of the lake, but it possessed zero tolerance for compressive mechanical loads. A steel cable tightening against the linen skin would act like a wire cheese cutter, slicing through the fabric and crushing the delicate wooden formers underneath. The solution required inverting the load dynamics. Instead of squeezing the aircraft, the team had to suspend it. This required the deployment of a specialized piece of hardware known as a spreader bar. The concept of the spreader bar is the governing geometry of high-value wreckage recovery. It is a rigid steel frame, typically rectangular or I-beam shaped, that is suspended from the surface crane. Its width matches or exceeds the width of the aircraft. By placing the lift points on this rigid frame wider than the target, the cables dropping down to the wreck hang perfectly vertical. This vertical geometry is critical. It eliminates the inward crushing vector that occurs with a single point lift. The spreader bar takes the compressive load so the artifact does not have to. For the Vindicator, the team designed a rigging plan that transferred all the lift energy into the metal center section of the wing and the forward fuselage. These were the components built to withstand the high G forces of a dive bombing pullout. The fabric sections were left to hang in tension, which is the only load direction they could still tolerate. Before the rigging could be attached, the divers had to prepare the connection points. This involved working in the zero visibility mud at 130 feet. The aircraft was not sitting on top of the lake bed, it was settled into it. The main landing gear had sunk into the silt up to the axles. This created a significant problem known as mud suction. When an object settles into fine sediment, the water between the object and the mud is displaced. To lift the object, that water must flow back in to fill the void. If the lift is too fast, the vacuum created under the object resists the motion, adding thousands of pounds of effective weight to the load. This phantom weight can snap cables or tear airframes apart. The divers used water jets to carefully clear the silt from around the landing gear and the wing roots. As they exposed the wheels, they encountered a fringe detail that defied the logic of 47 years of immersion. The main landing gear tires were fully inflated. They held the same air pressure that had been pumped into them by a mechanic in 1943. This was not just a curiosity, it was a variable in the lift physics. The air inside the tires created a localized pocket of buoyancy. The wheels wanted to float. They were held down only by the weight of the steel struts and the grip of the mud. This buoyancy meant that once the suction was broken, the aircraft might spring free from the bottom rather than lifting dead. The rigging process was a tactile exercise in the dark. Divers threaded wide nylon straps through the designated hardpoints on the metal wing section. They had to ensure that no part of the strap rubbed against the fabric skin of the fuselage. Padding was placed at critical junctions, but the primary protection was the geometry itself. The cables rose vertically to the spreader bar, hovering above the wreck, ensuring that nothing touched the linen sides. The aircraft was being cradled, not grabbed. Once the rigging was secured, the signal was sent to the surface to begin the tensioning phase. The crane operator took up the slack slowly. The goal was to bring the cables to a taut state without actually lifting the plane. This allowed the divers to verify the geometry one last time. The spreader bar hung level. The straps were vertical. The fabric was clear. The breakout moment is the highest risk point in the bottom phase of a recovery. The crane applied tension, gradually overcoming the static weight of the aircraft and the grip of the mud. The mud suction yielded. The Vindicator broke free from the silt that had held it since the Second World War. The inflated tires, which had acted as anchors in the mud, now contributed their buoyancy to the ascent. The aircraft rose straight up, remaining in a flat attitude. The lift was controlled to be agonizingly slow. The aircraft was not just a solid object, it was a container filled with water and silt. As it rose, the real risks were load transfer and differential forces, suction release from the sediment, shifting trapped silt and water that added unpredictable weight, and any trapped air pockets that could expand as pressure decreased. The lift had to stay slow and controlled to avoid shock-loading fragile stations and to keep the airframe stable through the transition. The preservation of the structure depended on equalizing the pressure between the inside and the outside of the airframe. The Vindicator cleared the bottom and began its transit through the water column. The spreader bar did its job. The cables remained vertical, and the fragile aft fuselage hung suspended in the current, free from contact. The operation had successfully engaged the metal skeleton while bypassing the linen skin. The aircraft was no longer a wreck on the bottom, it was a payload in suspension. But the environment was about to change again. The stability of the deep water was left behind, and the transition to the surface introduced a new set of forces that the spreader bar alone could not control. The rig was set and the geometry calculated, but the transition from the stable bottom to the surface introduced a final critical decision. The interface between water and air is a physical barrier that imposes a violent change in structural loading. For the recovery of Bureau number 1383, this boundary represented the single point of maximum failure risk. As the crane slowly retracted the cables, the Vindicator rose from the stability of the deep water toward the surface. In the water, the aircraft was supported by buoyancy, which canceled out a significant portion of its mass. The doped fabric skin was equalized with the water pressure surrounding it. But as the aircraft breached the surface, that support vanished instantly, replaced by the full force of gravity and the drag of surface tension. The air-water interface imposed a new failure mode. Buoyancy support vanished, surface tension added drag, and wave slap introduced cyclic loading. Exactly the kind of uneven stress that waterlogged fabric structures cannot tolerate. The surface tension of the water acting on the 42-foot wingspan created a suction force that tried to hold the aircraft down. If the crane pulled too fast, the drag would strip the fabric from the airframe. If the crane pulled too slow, the wave action at the surface could hammer the fuselage, causing the skin to buckle and tear. The lift operator executed the transition with a focus on continuous motion. The spreader bar geometry maintained vertical alignment, preventing the rigging from crushing the fuselage. As the propeller hub broke the surface, the water poured out of the engine cowling. The drainage was critical. A cubic foot of water weighs 64 pounds. The wings and the aft fuselage were essentially hollow containers. If the water remained trapped inside as the plane entered the air, the internal weight would exceed the design limits of the rib structures. The aircraft had to drain at the same rate it rose. As the landing gear cleared the surface, one detail fit the low energy loss profile. The tires still held pressure. It was consistent with a relatively gentle water entry and long protection from ultraviolet exposure. In sunlight, the 9-B-12 code became readable without lamps, a surface world confirmation of what the survey had already proven. But the exposure to the atmosphere triggered an immediate new constraint. In the water, the aircraft was chemically stable. In the air, the drying process began instantly. Rapid drying of waterlogged organic materials causes the cellular structure to collapse and shrink. If the linen skin dried out in the sun, it would shrink uncontrollably and tear itself apart, destroying the forensic value of the artifact. The decision logic shifted from extraction to stabilization. The objective was not to dry the aircraft, but to keep it wet. The recovery plan dictated that the aircraft could not remain exposed on the deck of the salvage barge. The team had prepared a preservation protocol that required keeping the airframe cool and shielded from direct solar radiation until it could be transported to a controlled facility. The successful extraction was not the end of the danger, it was simply the exchange of one set of environmental threats for another. The crane swung the dripping airframe onto the deck of the barge. The Vindicator sat heavily on its landing gear. The structure held. The spreader bar was lowered and the tension on the nylon straps was released. The operation had succeeded in moving the object from a high-pressure, deep-water environment to a one-atmosphere surface environment without compromising the structural integrity. The fabric was intact, the wings were level. The unique transitional design of the 1939 airframe was preserved. The external condition of the aircraft was now a known quantity. The lift had proven that the recovery of a fabric-covered aircraft from deep water was mechanically possible. But the true scope of the preservation was still hidden inside the cockpit. The exterior had been subjected to the open water of the lake, but the interior compartments had been sealed by the canopy and the fuselage structure. As the Vindicator broke the surface, the interior compartments revealed a level of preservation that surprised even the salvage team. Standard forensic logic dictates that organic materials submerged for 47 years should be reduced to pulp. Paper is wood fiber held together by weak chemical bonds that dissolve in water. Steel rusts in aluminum pits. The expectation for a cockpit interior exposed to a lake environment is a cavity of mud and corroded control linkages. But the recovery of Bureau number 1383 contradicted this baseline assumption. When the conservation team accessed the interior of the Vindicator, they found that the lake had not destroyed the evidence of the 1943 flight. It had suspended it in a state of arrested decay. The cockpit was a sealed volume. The canopy had remained closed, and the fuselage structure had prevented the free flow of current. Inside the pilot station, the team found the map case used by Second Lieutenant Lemons during his carrier qualification attempt. Inside the case were the navigation charts for the Lake Michigan training area. They were wet, but they were legible. The paper had not disintegrated. The text and the grid lines were clear. The level of preservation extended to the smallest mechanical details. Clipped inside the map case was the pilot's mechanical pencil. It was not lying loose on the floor where a crash impact would have thrown it. It was still secured in its holder. This fringe technical detail provided a definitive confirmation of the impact dynamics. The aircraft had not struck the water with violent deceleration. It had entered the water with enough grace that a pencil remained in its clip. The cockpit did not look like a crash site. It looked like an operational station that the pilot had simply stepped away from. The recovery of these artifacts marked the end of the salvage phase and the beginning of the restoration phase. The aircraft was transported to the National Naval Aviation Museum in Pensacola, Florida. The transition from the cold, dark environment of the lake to the warm, humid air of the Gulf Coast required immediate stabilization. The restoration team faced a critical timeline. The iron components, which had been stable in the low oxygen silt, would begin to oxidize rapidly upon exposure to the atmosphere. The doped fabric, which was still flexible when wet, would turn brittle and crack if allowed to dry unevenly. The restoration process was not a repair job. It was a forensic disassembly. The team spent 9 years working on the airframe. The effort consumed 20,000 man-hours of labor. Every component was cataloged, cleaned, and treated with corrosion inhibitors. The objective was not to make the aircraft look new, but to preserve the original materials wherever possible. The fabric covering on the aft fuselage was carefully cleaned and stabilized. In a standard restoration, old fabric is stripped and replaced with modern synthetic materials. For Bureau number 1383, the retention of the original 1943 linen was a primary directive. It was the physical proof of the aircraft's history. The preservation of the Vindicator solved a gap in the engineering record. Because every other example of the SB2U series had been destroyed, This airframe was the only three-dimensional data point for the design. Historians and engineers could study the transition from tube and fabric to monocoque metal construction, not through blueprints but through the actual hardware. They could see how the Vought engineers had mated the steel tail structure to the aluminum center section. They could examine the specific rivets and welds used in 1939. The aircraft was a Rosetta Stone for a lost generation of naval aviation technology. The legacy of the operation is defined by the completeness of the artifact. Most underwater recoveries yield fragments or corroded skeletons that require substantial reconstruction. The Vindicator is displayed today as a complete aircraft. The tires that rolled off the deck of the Wolverine are the same tires on the gear struts today. The instrument panel contains the original gauges. The preservation is so absolute that the aircraft effectively traveled through time. The success of the mission validated the logic of freshwater recovery. It proved that under specific conditions of depth, temperature, and sediment, the destructive clock of corrosion can be stopped. The lake did not act as a destroyer of the aircraft. It acted as a steward. It accepted the machine in 1943, held it in a protective envelope of cold darkness, and released it 47 years later. The recovery team provided the geometry and the rigging to bring it back, but the environment provided the conditions that made the return worth the effort. The project closed the loop on a loss that occurred during the height of the Second World War. Second Lieutenant Lemons survived the accident and the war. His aircraft survived the peace. Today, Bureau Number 1383 stands not as a memorial to a tragedy, but as a testament to the discipline of forensic engineering. It is a machine that was lost to the water and reclaimed by science, proving that with the right procedure, even the most fragile history can be brought back to the surface.